Yeah, so the graph is going to split at -1, so I'll give myself a little guideline at x equals -1 with an invisible dashed line there that on the left side of that we're going to have one graph, on the right side of that we're going to have the other graph. This x is less than -1 is the left side of this line. So on the left side of this line, I'm going to graph x plus 1. So easiest, quickest way to do that would be to do a quick xy table. If you don't want to mess with the slope and the intercept and all that, you can just start plotting points to the left of that line, like -2, -3, and -4. When you plug in those numbers into this first function, we just add 1 to them. So this will be -1, this will be -2, and this will be -3. So I can start by plotting those points, -2 comma -1, -3 comma -2, and -4 comma -3. So it looks like the line is going down this way. Now, what happens at the red dashed line is also important. So we should, even though this says x is strictly less than, and it doesn't have the little equals to sign, we should still plug in -1 into here, but keep in mind that whatever we get from this is going to be an open circle on the graph, because we're not going to reach that point. So when we plug in -1, we get 0, which is here. So we're going to put an open circle there, and then we're going to go all the way up to that open circle. And that's where our graph is going to switch to the other graph. Now, it may or may not switch from that point exactly. It may fill in that gap and go in a different direction. It may start somewhere else and go in a different direction. I don't know yet, but I know that this graph, if I'm going from the dashed line to the left, it goes like this, open circle, and down and to the left like that. This was for the x plus 1 equation. So then for the other one, I would make another table. Y equals -2x plus 1. For that one, we're going to plug in numbers greater than or equal to -1. So I would start at -1 and then move to the right on the x-axis. So -1, 0, 1, 2. I would plug in some of those points. 0, 1. We probably don't need too many. If you recognize this from your functions as being a linear function, a line, then you don't necessarily need too many points, because all you need is 2 points for a line. So -1 plugged into this equation would be -2 times -1 is +2. Plus 1 is going to be 3. So we get 3 when we plug in -1. When we plug in 0, we're going to get 1. When we plug in 1, we're going to get -2 plus 1 is -1. So let's plot those points. -1 comma 3 is going to be a solid circle up here, because again we are including that in this second piece of the function. 0 comma 1 would be here, and 1 -1 would be here. It looks like those are all in a straight line, so I'm just going to draw my straight line here, and I know the XYZ homework kind of draws it for you when you plot the points. You just need to worry about the open circle, closed circle situation at these two specific endpoints. So we got our left-handed ray over here with the open circle, and we got a right-handed ray with a closed circle. Does that help a little bit with your...
Yes, thank you.
Nice. Any other questions on this or any other homework problems? Oh, I guess we should answer the domain question. Give me a sec. The last part of the question asks for the domain, which is all of the... Whoops. Why did those go... Okay, well, I'm going to move those to the side. It is asking for domain, so... where are they? Oh. Okay, it's going to be almost impossible to place it back on the right spot now, so... What was your question? Sorry.
So for y equals negative 2x plus 1, for that one we it's a negative 2 times whatever the number that we have.
Say that one more time.
So the y equals negative 2 times plus 1
Yeah.
is we get negative 2 and multiply it by one number that we have on the y.
Yeah. Are you asking about how we plugged in the numbers in the table?
Yeah.
Yeah. You just plug them into x. So if this is -1, this -1 goes into the x, replaces the x. So -2 times whatever number, and then a +1. Is that what you're asking?
Yeah.
Okay, yeah. You plug it in like you would, like if you're doing f of -1, right? You plug in -1 for x.
Okay, thank you.
Okay, we should talk about the domain at the end of this, which is if I go from left to right, which x values do we have along the blue line and which x values do we not? Are there any x values that we skip along this whole blue two-piece line? The only place we might skip a number is the -1, right? But do we have a point on the blue line at -1? X equals -1. It's a yes or no question.
Yes.
Yes, and it's right here, correct? It's the -1 comma 3. So the only place we might have a skipping is here at this red dashed line, but we don't skip there because we do have a point there. So the domain here is going to be -infinity to +infinity, or all real numbers. I don't know how the XYZ wants you to put that in.
So the domain is infinite.
Yeah, -infinity to +infinity.
Just because they're both going down, like.
No, it's because we're going left and right infinitely.
Oh. So the parentheses. Why do we have the parentheses again?
That's how we write interval notation.
So what about the half square parenthesis thingy? It would be one.
That we only use parentheses for infinity.
Oh, okay.
When we have solid numbers, then you look at whether it's included or not.
Thank you.
All right. Any other homework questions?
Wait, if I'm having trouble with the homework, I just come back to class. Then you help me with it.
Yeah, I'll kind of take 10 minutes, 15 minutes at the beginning of class on Wednesday and Friday as well, in case anyone has questions.
Okay.
But yeah, you guys should be working on the XYZ homework. You should be registered on there. You also need to get your hands on the workbook. I know the bookstore has them in stock, so you need to get your hands on the workbook. They do have it. They should have it in stock. They told us they had it on the floor, like on the shelves at the physical bookstore today, or last Thursday. They say they got it in a shipment, so they should be out on the floor now. So get your hands on the workbook, because I'm not allowed to post any more of the workbook. I posted 1.4, section 1.4, which we'll be going over today. So if you didn't print that, go ahead and pull that up on your computer so you can look at it while we work on it. Take notes on a piece of paper, and then you need to get your hands on the workbook by Wednesday or Friday latest. Okay, we're going to go into, hopefully watch the videos on 1.4, which is the composition of functions. We're going to review this by doing some of the examples and leaving some of the examples for you to work on. And then I also have a worksheet on Canvas for you guys to work on in your groups after we're done going over the workbook examples. Composition of functions. Okay, let me do this first example. It doesn't really have to do with composition of functions yet, but it is a very common function that you may have already seen. In 1.2, I think we did something like this with one of the examples. So let me do this one so that you have something to look back to when you start seeing this kind of difference quotient show up in your homework and stuff. So how do we evaluate this function given 3x plus 2 with these given parameters? So first, let's take it piece by piece. I'm going to do some highlighting here to keep track of things. I'm going to do this one in blue highlight and this in orange highlight, and then so we'll highlight the pieces as we go. So the blue highlighted expression, the f of x plus h, that's telling me to plug in x plus h instead of x, right? So I'm going to take this x plus h and I'm going to put it wherever I see an x in this 3x plus 2 expression. So instead of writing 3x plus 2, I'm going to write, I guess I'll rewrite the expression first. X plus h minus f of x all over h. So instead of f of x plus h, we're going to write 3 times, and instead of writing 3x plus 2, instead of x, we're going to put x plus h. And then a plus 2. So this is the blue highlighted expression. And then we have a minus, and then the yellow highlighted expression, which is, or the orange highlighted expression, which is f of x, is just saying take the function f of x and put it there. Don't replace the x with anything. Just the 3x plus 2, and that is our yellow expression. And then don't forget about the all over h part of that. And now we do some simple algebra. We distribute this 3 into this expression. We are going to distribute this -1 into the second parenthesis here, because there's a negative sign in front of a parenthesis, so that's essentially a -1. So we'll distribute that. We'll have 3x plus 3h plus 2 minus 3x minus 2 all over h. Do we see things that cancel? Yes, we have a positive 3x and a negative 3x that are going to eliminate each other, and a positive 2 and a negative 2 that will eliminate each other as well. So we end up with just a 3h on top and an h in the denominator. And then finally, h divided by h goes away because h divided by h is equal to 1. So we end up with the number 3 here when we simplify, or 3 over 1, which is equal to 3. All right, next thing we can actually get into, oh, not yet. I thought we were going to start combining functions, but we're not. I mean, we're going to composing functions, but first we're going to talk about how to combine functions like addition, subtraction, multiplication, division. We have some new notation here. That's all this is. This is introducing notation of, if we were to write f plus g, f and g representing different functions of x. If I were to write f plus g of x, that's simply just adding the two functions together separately. Okay, so it's just a new way of writing. Instead of writing f of x plus g of x, writing the of x part twice, we'll just separate that out, and just write f plus g. Same thing with f minus g, f times g, and f divided by g. So this whole box is just notation. What this f plus g, what the f plus g and f minus g, all of those represent in terms of the individual functions f and g. Given f and g, evaluate each of the following. So let's look at what the notation is or does. Let us begin by, we'll do part B. I'll do part B here since that's the more interesting one. You guys can do part A on your own. This is telling me to take g of or g and divide it by f. So we're going to take g of x and divide that by f of x. Right? And g of x and f of x are given to us in the question here. We have our g of x and we have our f of x. So we're going to take those and we're going to substitute for each respectively. So g of x in the numerator is x squared minus 1. In the denominator we have an x minus 1. You should recognize one of these functions as a quadratic, a factorable quadratic. The numerator here is the x squared minus 1. You should know how to factor this from your algebra courses. So this, let's make a note of it here while we're at it. So that's our f of x. This is our g of x. Let's make a note of this. This is what we call a difference of squares. And it factors into two parentheses as x plus 1, x minus 1. If you don't believe me, feel free to FOIL this out, the x plus 1 and the x minus 1. You can multiply that out. You should know how to multiply. And you'll get back to this x squared minus 1. So we can split it up into two parentheses. The reason for doing so would be to see if anything cancels, if there are any similar factors. And we see the x minus 1 fully show up in the numerator and denominator, so we will cancel those and end up with just x plus 1 as our simplified expression for g of x over f of x. Okay, and then finally we are going to learn how to compose functions. So here we talked about 4 operations on 2 functions, right? We can add functions together, we can subtract, we can multiply, we can divide. These are things we can do with regular numbers as well. We can add, subtract, multiply, divide. We're going to get into a new type of operation which is called composition of functions. Which is what we do when we put one function inside of another function, because a function has an operation of its own where we start plugging things into it, right? In this first example, we plugged in x plus h into this function, for example. So if we can plug in simple expressions into functions, that means that we can also plug in functions into other functions. So let's see what this example... this is an example that's solved for you. So let me actually go through that. And let's talk about what this new symbology is and what the definition is saying. When we see this open circle symbol between 2 functions, this is referred to as, or this is read as f composed with g. And we simply take g of x and we plug it into f of x. So because functions have a new way of working with them, which is inherently just plugging things into them, we're going to take functions and plug them into other functions. So let me do, which one do I want to do here? I definitely want to do part B. I'll do A and B so that I can get you guys started on these. So part A, evaluate f of g of 3. So what's happening here? Let's try to break this apart. F of g of 3 when you're working with these compositions of functions, you're going to want to start from the inside out, just like how we work with parentheses in algebra. If you were to have, you don't need to write this down. If you were to have like a, I don't know, 3 times 4 plus 9, something like that, you would essentially start with the inside of the parenthesis, evaluate that, and then move outside to the outside of the parenthesis. So we're going to start with the inside of the parenthesis, which is the g of 3. So we're going to evaluate that first. Evaluate first. Meaning, how do we evaluate g of 3? Well, we just plug in 3 into g, right? So we leave this f part alone on the outside. And instead of writing g of 3, I'm going to start writing what g of x is, but I'm going to plug in 3 as I'm writing it. So 3 minus 3 squared. And we'll just, these are just numbers, so we'll simplify those. F of 3 minus 9, which is f of negative 6. And then we're going to plug in, this is telling me to plug in negative 6 into f of x, which will be 2 times negative 6 plus 1. And that's coming from the function f, right? It's 2x plus 1. So we plug in negative 6 for x, which gives us negative 12 plus 1, which is negative 11. So this is an example where we plug in we have a composition of functions, but inherently we're just evaluating it for a number. So we can just start from the inside, evaluate the inside function with that number, and then evaluate the outside function with the resulting number, which was negative 6. Second example is a little bit more involved because we are not working with a number. Instead, we're just working with x. So we're going to work from the inside out, but we're going to be plugging functions into functions here when we do this one. So f of g of x will be f of, and instead of g of x, I'm going to write out what g of x represents, which is 3 minus x squared. And I don't have a number to plug in for x, so we'll just leave it as is. And this is now telling me to take this 3 minus x squared and plug it into f of x. So we're going to plug it in for the x there. So it'll be 2 times 3 minus x squared plus 1. And we've essentially done the composition part of this problem. We just need to maybe simplify the expression a little bit. We'll distribute this 2 and see if there are any like terms we can combine, right? So 2 times 3 is 6, minus 2 times x squared plus 1. We can combine the 6 and the 1 to make a 7, minus 2x squared, and there is nothing else to do with that. So we'll just box it there.
Are we getting the 2 from the 2 times 3 times a minus x or something.
Where is this 2 coming from?
Yeah.
It's from f of x.
Oh,
So you see how this is essentially the same as this, but we've just replaced the x with this 3 minus x squared.
okay. Wait, let me see. Okay.
Okay, you guys can try the other ones on your own. Using the tables below, evaluate each of the following. I will just do one of these. I'll do part A, so you can do the rest. F of g of 1. We have 2 tables here, right? It's important to identify the tables. First table is a relationship between x and f of x. Second table is a relationship between x and g of x. So we're going to do the same thing we did last time, but instead of having a, like, you know how we plugged in this plugged in this number 3 into this function here, instead of this function given to us, we're given it in a table format. So this is a relationship between x and g of x, right? And this is a relationship between x and f of x. Instead of being given explicit functions or expressions to work with, we're given a table instead. So if I wanted to figure out what g of 1 was, how would I do that?
You simplify?
Where do I find g of 1?
The x?
What do you mean?
The x value.
Is what?
See it on the x value.
Okay.
Which
table do we use for g of 1?
The fx.
Why? No.
Oh, the x?
No. There's 2 tables, right? There's the f of x table and the g of x table. If I want to evaluate g of 1, we're going to evaluate using the g of x table. How we're going to do that is this is telling me that the x is 1, and it's asking me what the g of 1 is. So if I plug in 1 in for x, what do I get for g of x? Where in this table would that be?
You get 1.
Where do you see that in the table?
Because are we going to plug 1 to g?
Yes.
So,
X is 1. So when x is 1, what is g of x?
1.
3.
3.
Oh.
So the table tells you each x value and its corresponding g of x value, and then each x value with its corresponding f of x value, right? So once I replace that g of 1 with a 3, because that's what that is, now we want to evaluate f of 3. So using the f of x table, if my x is 3, then my f of x will be 2. So we evaluate f of 3 to be 2.
Okay, I get this one.
All right, so that's how we use the tables. Let me go over one where we use graphs instead. So this is the 3 different ways we can look at functions and look at their values. So using the graphs below, evaluate each of the following. So it's a similar type of thing, but instead of a table for f of x and a table for g of x, instead we have a graph for f of x and a graph for g of x, which is just as good as a table, right? Because we can look at every x value, like we can look at x equals 3, go up to the line, figure out what the y value or the f of x value is for that x value, right? So we can do this same exact thing. Let's do part A, f of g of 1. If I want to evaluate g of 1 first, right? So we're going to evaluate g of 1 first. That we'll be doing that by using the g of x graph, and g of 1 means that x is equal to 1. What is the y value when x is equal to 1? So we'll go to 1 on the x-axis. We'll go up to the line. We're going to assume that hits nicely at 3, right? This is 1 comma 3. So when x is 1, g of x is equal to 3. So we'll replace this g of 1 with a 3, right? Just using this point on the graph here. If you want to put a point on the graph to remember where you got that from, 1 comma 3. And then we're asked to evaluate f of 3. So this will be using the f of x graph, and we'll be going to x equals 3 and going up to the line, figuring out what the point is on that line where x is equal to 3, which is 3 comma 6, which means f of 3 will be 6. So you start with the inside function, evaluate that using a graph or a table or an expression, and then you move on to the outside function once you've evaluated that. And you don't necessarily have to use both functions, right? We see an example here where we do g of 5. You're still going to do the same thing. You're going to evaluate the inside function g of 5. You're going to get a number result because that's going to be a point on the graph. And then whatever that number result is, we'll evaluate again on the same g function, the same g graph.
I didn't really get D.
You're going to work on D and see if you can figure it out in your groups. So if you can't figure it out with your groups, then I'll come help you with that. But this should give you an idea, part A should give you an idea of how to work your way through these problems. Okay, and then last thing we learned about in 1.4 is how to find the domain of a composite function. And here in the box, we have a simplification of what it means to be the domain of a composite function. The domain of a composite function, f of g of x, is the set of those inputs x in the domain of g. That's an important part. In the domain of g, for which g of x is in the domain of f. So how are we going to work with that? We're going to do two things. I don't know why there's a little apostrophe on that x. We're going to ignore that. What we're going to do is find domain of g of x and f of g of x. Simplified. That's going to be the kind of the way we're going to find the domain of the composite function. Right, so the simplified version of f of g, if it does simplify, we'll simplify it, find its domain, and then we'll also find the domain of g and kind of combine those together to give us a single domain. So
So with the ones with domains or something like that, do we have to always simplify?
yes, you always have to simplify everything as a general answer. Let's do this example where we find f of g of x and then we'll find its domain. So this composition, f of g of x, means we're going to do f of g of x written this way, right? If I rewrite it in our known notation. And that's telling me to take my g of x and put it here in this parenthesis. So it'll be f of, and g of x is given to me as 1 over x in the question. And now we're going to plug in 1 over x into f. So we see f here with the 1 over x minus 4. Instead of x, we're going to put 1 over x in that expression. So we'll have 1 over x minus 4. Continuing along, we should probably simplify this a little bit. Easiest way to simplify this would be to multiply the whole numerator and the whole denominator by x, because we have fractions within fractions and we don't really want fractions within fractions. So we'll have x over 1 minus 4x when we do that product. And that is our composition simplified. And then, like I said, we're going to find the domain by finding the domain of G and finding the domain of this simplified composition separately. So domain of G, what can you tell me about the domain of G? What are some things that might be an issue with G of x?
B can't, or X can't be equal to 0.
Good. X is not equal to 0. We'll just write it like that for now for shorthand. We don't need to do the whole interval notation at the moment, because we're going to combine this domain with the other domain as well. And then the domain of f of g of x. What about that? What can you tell me about the domain of the simplified version? I guess I should put simplified there. What can you tell me about the domain of this expression here, the x over 1 minus 4x?
X can't equal 1 over x.
Where are you getting that? You said x can't equal 1 over x? Why is that?
Because wouldn't it make like the function like it would make the bottom of the function equal to 0.
How did you get to this is my question. Because you're right. Because you're right. What you're saying is correct, but I don't know how to get there.
Because I'm looking at the bottom, and 4 times 1 over x is equal to 1, and then 1 minus 1 would equal 0.
I see. But we don't want this bottom to equal 0, right?
Yeah.
Okay, so let's do that. Let's say it can't equal 0, and then go from there. Is that what you did?
Yeah.
Okay, so let's do that. We'll subtract 1 from both sides, right? Or I guess we can just add 4x to the other side as well. So 1 cannot equal 4x. You may have made a simple mistake in there somewhere, because if you do this and you divide by 4, you get that x can't equal 1/4. Is that what you meant to say?
Yeah.
Okay.
It can't equal 1 over 4.
Yeah. So x is not equal to 1 over 4. So we get that by taking this denominator, setting it equal to 0, like we did for domain, and getting down to x can't equal 1/4. So we have two pieces of the domain here that we need to combine. So the our final domain answer will be that x cannot equal 0 or 1/4. So we combine those two domains into a single domain, because in this composition operation, in this result, this is a single function, but it's coming from a composition of two functions. So when we compose this, we need to make sure that the domain of g is satisfied and the domain of f of g simplified is satisfied. So x can't be either of those numbers, otherwise this composition falls apart, right? If x is equal to 0, then the inside of this function falls apart. If x is equal to 1/4, then the simplified composition falls apart. So x can't be 0 or 1/4 in the end. So we gotta combine
on
these
a
two.
test, we could answer the question like that. We don't need to do interval notation if it says minus domain.
If the question says to do interval notation, yes, you do. So let me write it in interval notation as well then. It's a great question. So let me box that and we'll move it a little bit. We'll say or. Or we can write it as, this is going to be a long interval notation. But if the question says to write it in interval notation, we do. So, or it'll be -infinity to 0. And then we pop out 0. So we skip over 0, go to 1/4. Also pop out 1/4. Go to infinity, right? So to not include a number like 0, you just split your interval notation at 0, and you split your interval notation at 1/4, so that those are not included in your answer, in your domain answer. So either one of those notations could be okay, depending on what the question says. If the question doesn't say what notation to put it in, yeah, you can leave it in the easier to write notation.
All right, thank you.
So do we always have to put the interval notations or no?
If the question says.
So the interval notation is something like that. Like if it's 0 or x or something, is it infinite?
I don't know what you're asking.
Because we're getting infinite.
Yeah, because x is just not supposed to equal these numbers. So to represent everything else, we need some infinities in there.
Okay.
Right? It might help to do a number line. It might help to take this and put it into a number line. And say at 0 and at 1/4, I want to have holes punched out, but I do want everything else going this way forever. I want everything in between, and I want everything going this way forever, right? And you should be able to put that number line into this interval notation down here. All right, so if it helps to draw a number line, do that. This number line shows there are three pieces, right? There's this blue shaded piece on the left here. There's this blue shaded piece in between the two numbers, and this shaded piece to the right here. So those are the three pieces of my interval notation. Okay, and then the last thing we do in this section is to decompose a composite function. I'm just going to leave you guys to work on that one. And if you need help, let me know. You're essentially given a single function, and you're supposed to split it up into its two parts and write two functions, so that if I were to compose those two functions, I would end up here. So like it's splitting the function up into its different components. Okay? Right, so that brings us to the end of 1.4. Are there any lingering questions from the whole thing that you were curious about?
No, I am when I get to them.
Anyone else?
Are we gonna get a worksheet or is it on the workbook?
Both.
Oh,
You're gonna do. So I'm gonna put you into workout breakout rooms. You guys will be working on the examples that I skipped, as well as the worksheet on Canvas. Let me see what the worksheet looks like. The worksheet has some stuff from 1.3 as well as 1.4. So if you want to just work on the 1.4 questions on the worksheet, it's going to be the second half of the worksheet where the numbers start over. I don't know why the numbering is weird. But on the bottom half, there's a number 1 and a number 2 on the worksheet. Those are the, I guess I can show you the worksheet. On the bottom half, there's a number 1 and number 2. This bottom half of the worksheet deals with 1.4. So if you want to work on those in class and ask questions, numbers 1, 2, and 6 on the worksheet have to do with whatever we did last week on Friday. Okay, so this worksheet is going to be due tonight by midnight, so get as much of it done as you can in class, I guess. And if you finish the worksheet, then go back and finish the examples in the workbook, or vice versa. You can do this in either order you want. Okay, so let me make those rooms.
wait, for Friday, were we doing a worksheet Friday?
We did not do a worksheet Friday. No, that's what I was saying. This is the first half of the worksheet covers Friday's material, and the second half covers today's material.